All right, easy peasy. Wait, I'm sharing
gonna
this
be
screen, right? You
hard.
see this moving?
Yeah.
All right.
Yes.
Yeah, for some reason the screen share is on the wrong monitor, but it's technically the right thing, so I don't really care that much. All right, so we'll start here. So this is actually no, this is the stack tracing one. We'll save that. We'll start over here. This is the spring 2019 exam. We have the spring, the fall 2019, and then we have the fall 2018. And then if you go back to 2018, you'll find that there are actual stack tracing problems, which is what we should expect to replace these problems since these won't be on the test, which would be the pipelining and risk processor. You won't see these, you'll see stack tracing instead. So make sure to keep that in mind when going over these exams. Also, you won't see stuff like this. This is also has to do with pipelining and such.
You also won't see latches as well, right?
Yeah, I don't think so. If we, as she said, if we haven't had a homework on it, it's a decent guess to assume it will not appear on the exam, which is
Okay.
a fair way to do this. All right, so starting through all these things, when it comes to answering these questions, it's almost always just the vocab slide she has at the beginning of each class when we start a new topic. So assuming her annotated slides are posted before the exam, which they tend to be, a good way to review for these things is to just jump back to one of her, open up her PowerPoints or whatever, her annotated ones, and then just find that slide and just essentially memorize it. Because
Yeah.
you'll find like for this one, like number 1 point, blank RTL describes what can be done in a single clock cycle. This would be the famous concrete RTL. Describes what can be done in a single clock cycle. So this is the shorthand that you're writing, which is then explained later with your control signals. So how do you achieve that concrete RTL statement? You use the accompanying control signals, and that's how you achieve what you describe. So that's what this is. So a concrete RTL describes what can be done in one clock cycle. Then we have a blank represents the organization of the computer in terms of registers, functional units, and buses. So this is actually microarchitecture. So we also have nano architecture and stuff like that, but I don't think we'll deal with that because that was a niche slide, and I don't think since we haven't had a homework, it shouldn't appear. But as said, these are just vocab terms. There's not too much to explain since once you know them, they're self-explanatory to a point. So we have 3, which is microprogrammed control is the alternative to blank control. So microprogrammed is the alternative to hardwired. So when you think of like a microcontroller or microprogram control versus hardwired control, I view hardwired as like actual logic gates that will do the same thing regardless as a hardware solution versus microprogrammed, which means you can alter the control structure if you so desire. So it's like the difference between an Arduino and an FPGA is also, it's hardwired, but you can change it. So it doesn't really matter, but either way, one's got hardwired control. So think of it as set in stone to a point, and then microprogrammed is, fluid. You can change the rules if needed. And then number 4 is true false. Blank, the amount of time it takes to execute a single instruction will decrease as a result of pipelining. So for 4, what do you guys think the answer is to this one? Because she talked about pipelining, and since it appeared on this exam, I don't know if this specific question will appear because she said pipelining is a no-go, but just in case, do you guys remember what she said regarding the time effect of pipelining, whether or not it actually shortens it?
Yeah, it does because it's like doing multiple tasks, at once.
So it actually doesn't shorten it. It simply starts the next series of instructions overlapping it, right? So here's the solution to this one.
Question.
Yeah, what's up? Yeah, what's up?
Yeah, no, I said it's a trick question then.
Oh yeah, it is a trick question because here you see here this is the type of question for pipelining and like risk processing that we wouldn't see on the exam, but it demonstrates what I mean about it not actually decreasing the amount of time it takes for a singular instruction. For a single, there's your trick, single instruction, because it doesn't actually change the rules of a single instruction, but it allows you to start the next series of instructions overlapping, which cuts down on the overall time aggregate. Or if it doesn't change the aggregate time, it at minimum changes the efficiency because it lets you do multiple processes more efficiently. So that's all that does. I'm on the wrong one. There we go. Pog. Let's go back up to the top. All right, that's false. And then we have 1 point here. The blank of a variable defines the range of visibility or accessibility within a program. So this is C++ terminology. This is the scope of a variable. So if anyone took, what is it like, what was the class 211, CPE 211 or whatever? That's the scope. You'll hear that word a lot all over the place in programming. This one we don't have to do because it won't appear. What is this? What is the time fully taken? We also shouldn't have to do this one either. There's a lot of questions here that we won't have to do because they shouldn't show up yet. And that mostly has to do with the timing. Anything that you see in her past exams with regards to timing like this, you can probably ignore because it shouldn't appear on the actual exam since we haven't done a homework on it yet.
It'll probably appear on the final exam.
Oh yeah, it's going to appear on the final, you bet. The final's going to be great because everyone's going to have forgotten about this little intermediate stage, which actually turns out to be roughly 50% of this exam, or it normally should be. So they're going to get smacked on the final when it turns out to be like 30% of the final grade or something.
Yeah.
So we'll have to go over that later, but we should ignore that for now. Ignore that again. All right, we can do the 3210 address machine stuff. Does anyone have any specific questions on how you would implement this function with 3210 or would like to see an example or something of this? Like, it doesn't have to be all of them. Like you could say, oh, I want to see how, like the pop and the push stuff works for 0 address and operating on the stack. Or, well, I mean, we're all used to 3 by now because that's what we've been doing in normal ARM assembly. All right, cool. So in general, pray for questions like this on the exam, because as long as you've done that homework assignment, you're pretty well set for these types of problems because all of us understand the order of operations. And
Yeah.
as long as you remember that, you're basically set.
Yeah, I feel like it's everyone, I think it's comfortable with that, and
Yeah.
we do,
Yeah,
hit
by
a lot
now.
of stuff like that.
But I knew a lot of people initially had some problems when you started getting down to the 1s and the 0s, but I think in my in the other video I explained some tricks for the 1s and 0s and 2s and such. It's just a new set of rules.
Honestly, for me, that was probably by far the easiest homework astagnment that we had.
It was quicker. I mean, there's a reason it's only worth 20 points. It wasn't meant to be a monster like some of the others, like stack trace. All right, so now here's something that we haven't done in a bit, but we did a homework on functions, but haven't done an actual exam on functions yet. So we actually have to do this proper, right? So we have to do functions, but in lieu of time constraints, we're not going to actually write the functions from scratch here. Instead, we're going to go over why the function she wrote works. So let's make sure these are the same. Nope, they ain't. Okay, wild. Bop, bop, bop. This should be it. Yep, go down here. So here we are. So, oh yeah, and this is the solution for her, 3 address stuff. In general, most most functions like this, you'll see that 3 addresses tend to hover around 5 to 7 instructions, and then it scales from there. These two are almost always like 1 or 2 commands apart from each other. It's just like a pattern thing. So there's a way to check yourself-ish. So we can go down here and begin. So this program adds to arrays. So luckily for us, she always initializes all the stuff for us in ARM, simply to simplify the grading for herself, which is understandable. There's 130 of us or so. So to start, oh wait, where's the C++ code? So here's all the initializations. And then we have an int I, so that's our index counter. And then we have a for loop, sets I equals to 0, I is less than size. Size was initialized where?
At the top, 10.
Yeah, 10, cool. And then we have an incrementer for I. And then it just adds, it adds index value of X to index value of Y, stores it into index value of Z, which is an empty array. And then what is this? Sign does what? It also writes a 0 into the array called sign if the sum, if the sum, what? If the sum is negative and a 1 into the array called sign if the sum. That's a confusing string of words right there.
Yeah. Okay. So it puts a 0 into the array if it's negative. 1.
And puts a 1 if it's positive.
Yeah.
Wait. So this is just, so Z is just gonna be 0 and 1.
Yeah. Yeah.
That's funny.
0, 1.
Okay. Well, there's one way to check yourself, I suppose. So we have conditionals for writing the zeros and the ones here. And do we even have a function here? I don't think we even have a function here, do we?
Compare load.
No, it's just a loop. I mean, you don't
Yeah.
have to write a function here. You could if you wanted to. Like you could write a function to do the else comparison for the signs, but you don't have to. So
I
the
have a
first things
question.
first. Yeah.
So if there were two loops on that right there, well, no, on the ARM assembly language, if there were two loops, how do we supposed to know where it ends and stops?
So
The
as in
loop
like
goes back-
if you're going down through here, you reach like loop to start. Like how do you know where like
Yeah,
the
what if it
brackets are
like,
for ending a loop?
yeah, what if there were like two and you only wanted that certain loop or
Yeah,
the
so
other one?
how the loops work is loops are controlled. Well, it's not loops. In reality, this is just like a marker, and the actual loop
Mhm.
is done down here. Well, it's done. Where is it? The actual loop here is done here. So
Yes.
it's actually branches and arm is what we call them here, but I keep saying loop because she wrote loop. As I said in a past video, this could be called hot dog for all the computer cares, as long as it's the same. If it said hot dog down here and hot dog up here, it would still function as normal. So the way to figure out where a loop ends is based on the branch conditional statement, right? So for here, we have a compare, and all this does is take R4 minus R3, and this sets our, what are they called? The CZV R, what are the, I don't remember. What'd you say?
The flags. It
Yes,
sets
the flags. They set the flags here. So particularly, this loop's conditional end statement is a branch greater than or equal to, right? So what really matters here is this equal to part, because that's probably going to get triggered before the greater than. That's just a conditional, just in case it were to skip the equal portion. But it's most likely going to trigger when the CMP is equal to 0. That is R4 and R3 are equal to the same number. So when they subtract the equal to 0, set the 0 flag as 0. And then it would immediately go down. This takes into account the flags and says, oh, 0 flag 0, that means equal to. Okay, go to done. Done down here, branch again, branches to done, and then it infinite loops down here, but the computer knows to terminate after a couple iterations of this, hence stopping your program. So that's how you actually, it's all about the conditional attachments onto your branch statements. So in this case, there is no conditional for this actual loop phrase here. See, it's just an unconditional loop. It will always, once this code runs through and reaches this B, it will always go back here. What stops it is this branch conditional statement that takes you to the done. So it's all about setting order precedence of
Yeah,
where your conditionals are set. The most common conditional I use to set those flags is CMP, which you'll see all the time. What were you gonna say?
I think there was well, the one I wanted to look on is on the fall 2019 on that one. It has two loops.
This is spring.
Has,
Oh, this is the wrong thing. I have fall 2019 right here.
yeah, it has two loops and it has like a
I went too
cube
far.
or something like that.
Yeah, I remember this one. I read through this one.
Yeah.
This one's a really interesting one. This one uses a function.
It said
This is-
loop A and loop B. That's how you can tell which loop is which. Same
Yeah.
thing as
Yeah, this one uses a function. So it's actually, this is a slightly more difficult one, as you can tell. It's more complex.
Yeah.
Oh, slurp some water down. All right. So for this one, let's run through this one real quick to discuss the logic of loops. This is a better example since it's more complex. So we have our variables initialized, right? And then we start at loop A, which sets the compare bit here, R4, R3. We have a conditional branch greater than or equal to, which will branch to done. So this is our termination value. So when this CMP sets the 0 flag, so if this CMP sets the 0 flag, or the what is it, the 0 flag or the negative flag, right? That would set either of those works, because negative flag means it's greater than, R3 is greater than R4, equal flag means it's 0. So if it sets either of those, most of the time it hits 0 before it hits greater than, depending on how you write it. Most people use this as an incrementer, so it's I goes up until I is equal to whatever, right? So it branches at the equal. So your first thing to notice is when R4 is equal to R3, R4 happens to be I, R3 happens to be size. So exactly, this is just, size is what you're setting. What is it? Yeah, so I is going to start out smaller here. wait, no, I is going to start out. The initialize I, yeah, I starts out smaller here. And then when I equals it, it's going to terminate. So it's immediately going to start. It's going to go down here. First iteration, nothing happens. But if this were to be equal to, it would immediately jump down here and we'd be finished. But it's not. So it starts by loading something from R8, loading something into R8 from this entry in R0, which happens to be the array X. This would enter 100 into R8 to start. This is a branch link. So this is how you know that there's a function. When you write a function, you use the branch link. So the system knows to store the next value of the program counter. So it'll take when you do a branch link, it'll store PC plus 4. So it knows when you're finished with the branch link to return here, as opposed to having to use some type of notifier up here. Oh, wait a second. There's 2 done be dones. Oh, so loop A terminates here, I believe. It goes to the first done. If it were to hit this.
It terminates there and then it terminates at the bottom too. So the way I always understood is the branch link will, while you're doing that, as you said, it's going to go down to cube and it's going to run through and then start loop B and run through and then go back up.
Yeah, that's how it should, because then it'll reach loop B will be compare, and then it'll branch greater than or equal to the back,
Yeah.
which back will move here. And here's your statement that moves you back. It takes the link register, which is what the whole branch link system is for, takes the stored value of link register, which happens to be PC plus 4, if I remember correctly, the original one, which would be this line right here, this store command, puts it into the PC or moves into the PC. And when you change the value of PC, it'll just jump up over here and you start at this line next. So one iteration of this system goes start, compare, continue. Compare, no, did not reach done. Go down here, load 100 into R8, branch link cube. Branch link stores something over somewhere else. Cube goes down to cube. We move a value of 1 into R9. We move a value of 0 into R1. We go to the loop B. We compare R1 with the number 3. As we know, R1 is 0 right now, so branch greater than or equal will not be tripped, so it won't jump back quite yet. It'll go down here, it'll multiply, do this math real quick, then it'll do this math, then it'll go to branch loop B, and it'll continue doing that until this is satisfied, this CMP satisfies branch greater than or equal. I believe that this would happen 3 times over, and then it would branch greater than or equal to back, jump down here. Now we're at back, executes this command, which is move, meaning copy the entry of link register into PC, which happens to be this line because it started up here since we're at the link. So whenever we do this, it goes back to the BL next line. So now we go to the store command, which will store the value of R9 into this entry here, which happens to be what? Is this the Z register, the Z array? Yes, it is. This will store it into the Z array first entry. And then it will go down here. And this looks like an incrementer of I, branch to loop A. And we'll keep doing that until I and size are the same. So this whole thing, the whole loop A portion, this will execute 10 times over. This will execute a lot more times because for each instance, it executes a couple times.
Yep.
So the total system executes, this portion executes 10 times total. This will execute a bunch of intermittent times for each cycle of loop A. So once you know how a program works for one iteration cycle, it's really just keeping track of numbers if you wanted to compute something by hand. For example, in the past exam, the program tracing, essentially this is what you had to do. You had to understand what an iteration of the program did and simply record values and keep track of values. But another thing you can do is you can plan out what you need to do iteratively wise for a function before you write the function. Of course, we're in a time crunch, right? So most of the time it's best to just start getting stuff down. But on average, we have no clue what type of program she could throw at us. It could be something like this, which is relatively more complex, or it could be something like this, which is relatively simple. It really all depends. But bank on this showing up, something that involves a function, right? Something that involves utilizing the link register, potentially something that even involves utilizing the stack. In fact, I'm pretty sure you could use the stack in this one if you wanted to, if you hate yourself. I don't recommend it. I hate the stack personally, but I understand why it's useful. Either way. So for the exam, it's best to go back and really review how to quickly write functions. Not even really review, just practice. Like just in general. Like the best practice is to open these exams up empty with no solution and just time crunch yourself. Try and get your program writing in under like 15-20 minutes. That consumes a decent chunk of time, but assuming the rest of the exams are structured, with questions like these, which are relatively quick compared to these, it's better. Another quick tip, I recommend taking the test in person if possible, because taking it in person gives you one major advantage, which is the fact that you can flip back and forth between the exam. So your answers aren't locked in, right? So I'm a big proponent of using the test to take the test. You can do this essentially anywhere. It's just a flaw of how human beings write exams, right? So there's information all over this thing that you can use if you're really keen. But in general, a good strategy for a test like this where the big questions are in the back and the air quotes filler or quick questions are in the front, start from the back. Get the hard ones done quickly and then go back up. If you run out of time, you lose like 10, 12 points here, as opposed to losing 20, 40 points down here because you ran out of time. It's better to work slow on the big ones than on the small ones. So that's just a general tip for these exams specifically. But we can go back here. So that's what these are function wise. So are there any more questions on how like tracing like loops and like the loop logic down, or is that relatively solid?
No, that's pretty solid. I'd say, like I said, I'd stay for the 2 loops.
Yeah, yeah, study this one. Best exam to study is probably the best exams to study is the fall 2018 and the fall 2019 and the fall 2018 right here, because 2018 has stack tracing, and this is definitely gonna. I wouldn't be surprised if we see 2 stack tracing questions or a stack tracing question worth like 30 points, honestly. So it's best to make sure that you are focused on that. We'll go over the stack tracing one in a bit. So that's what these look like. So let's scroll down past that and look at this one. So is everyone good on this? Because I'm fully confident that I could do this whole thing in 10 minutes if we really want to know. And if you want me to make it look pretty, I can do it in 15 by drawing on it if needed. So does everyone understand how, like, given a picture like this, or given a figure, you can, write some semblance of concrete RTL that works, and then, signals, air quotes, which are actually just, whatever it takes to open your floodgate and send your data signals through in a particular clock cycle. As well as don't forget that in signals, you always have to specify the function operation if you're utilizing the ALU. That's something that some people might mess up, so it's good to remember to do that. That's important. Are there any questions on something like this? The control processing or whatever. I expect to see 1 to 2 questions like this, probably 1, something very similar to this. We did a big homework assignment on this, and
I'd expect to see kind of like the homework where there's 2, where we had like one with like 2 buses and then one with.
I hope we
4.
have one with 2 buses. 2 buses are so much better. Having more buses, in my opinion, is more useful for most things. This one is annoying because people might miss this. R1 is hardwired into C. So it's useful for some operations and it's detrimental for others. So everyone needs to remember to really inspect your figure and understand where the connections go, because you could write something that if this weren't connected would work perfectly fine. But since it is connected like so, it'll completely mess up what you're doing and you can lose points for that pretty badly. And then down here, and then down here we have a more abstract one, which isn't quite, I know you use the same figure. So this is 30 points total, right? You have 20 points for writing some, what is this? Store IP R0. Yeah, in general, yeah, she is like, this always looks weird. Like whenever you get this, you're like, I've never seen this before. What does that even mean? But then it goes on to describe what it's actually doing and then shows you that it's actually this. And we've actually done something just like this, taking the double nested memory of some value. It just so happened last time we took a double nested memory store of R1, I believe, plus just R0 and stored it into like P on the homework.
Yeah.
But all right, I'll move on past these. I think everyone's got a decent grasp of these. One thing though, in general, is you need to understand the fetch cycle, because look, the 10 other points is use the same figure. How do you do the fetch cycle, right? And here's something to remember, just because she gives you, however many cycles doesn't mean you need to use all of them. This one you might have to use them because we only have 2 buses, right? 2 buses make the you need more clock cycles with less buses on average. So that's just how it is, unfortunately. So review what the concept of a fetch cycle is, which, just take your program counter and, go mess around in the memory and put something in the instruction register, essentially is all it does. So that's something important to remember. Just memorize the concept of a fetch cycle, not necessarily the commands, because that changes based on your hardware layout. Down here, risk processing, we don't have to do any of this. So we will move on to the stack tracing in 2018 because that's more important. That is the end all be all. A lot of people have expressed concern over the stack tracing. All right, 30-point problem, right, for stack tracing. So this matters a lot. Consider the following ARM program. Trace the values of the registers shown as they change during program execution. Also track the stack activity. Clearly indicate the value of SP, stack pointer, and the FP, frame pointer. Frame pointer is stored in register 11, right? Is that how they do it normally? I know in Kiel, they designate a register as SP with parentheses, but then there's also a register designated for FP in general. And I think that's 11, right? R11 is the FP in general, or that's.
Yeah, I think frame pointers are 11.
Yeah, so frame pointers are R11, so that's good to remember. Remember that frame pointer is R11, unless she designates that down here. Okay, never mind. She doesn't even carry. She just writes frame pointer, so you're fine here. She doesn't write stack pointer though, but that's because normally the frame pointer and the stack pointer tend to line up for most of a program. Let's go down here. There may be unused columns or rows in the table. If you need to add columns or rows, you may do so. This thing right here, almost always, I can almost guarantee you'll never need to add columns or rows. If anything, you'll have many more unused rows. All right, let's look at what this, here's our C statement for this, int factorial. So we have int main, it sets n equal to 1, sets some value or preserves some variable f. F's equal to factorial n, so that's a function that's written down here. Anytime you need a function, that's going to start messing around with the stack in general. Sometimes it depends on how you want to use your function. Goes down here. If n is equal to 1, return 1. Else return some function factorial, which takes the factorial of n minus 1, it looks like. So it has some command that it gives it to us. We don't have to write anything here. I got stopped up thinking this was a problem about function writing. All right, so we start out here. So first things first on a stack pointer problem, if you're taking this in person, you can have I recommend bringing a highlighter or something with you, because just like how we had in the homework where she would highlight certain commands, in general, if you're doing stack diving or stack tracing, it's a good idea to highlight what commands you suspect to affect the stack, right? So whenever you run through an iteration or something, you can be like, okay, well, this is going to affect the stack. Let's see how it changes it. So first things first, move the link register, shouldn't change anything. Move frame pointer might change something because the frame pointer messes around later on. Now this definitely changes something. Pushing the frame pointer is pushing this value that we just pushed into the frame pointer onto the stack. So these are one and the same. This doesn't necessarily affect the stack directly, but this value that has been moved into frame pointer is pushed onto the stack. So it's important to recognize what's in where and where it's headed. Sub SP8, this hasn't affected anything on the stack yet, but it's operated on the stack pointer, so keep that in mind. Add FP0, this hasn't changed anything on the actual stack, but it has affected values that relate to it, so keep that in mind as well. This just puts a value into R0. Branch link factorial, so this is going to set some branch link, could be important later, we'll keep a note of it. Store R0 F frame pointer plus 4. So this is just taking the FP value, which still happens to be, no, it's FP plus stack pointer, but the stack pointer has already been designated somewhere. So was it stack pointer plus 8 here? No, that's sub. Stack pointer minus 8 put into itself. Then the stack pointer is added to the frame pointer. And it was, what is this, plus 0 here? So that changes nothing. It just forces it in. So now we're at the store portion. Okay, so all this does. So this shouldn't affect the stack, right? Does anyone know if the store function will affect the stack? I don't believe.
I think it does.
Oh wait, yeah, you might be right here. It's gonna put it into the memory location,
Yeah.
right? And
The way I always kind of looked at it was moves, push, add, subtract, and stores all will affect it somehow.
well,
And
yeah, in
so
general, because for this one, you're operating. So the first thing, the move put this value, this memory point into the frame pointer. But this on its own won't do anything to the stack. The next line takes this value that was put into there, pushes it onto the stack. Down here, nothing overtly happens to the stack yet. We're just initializing the frame point or a stack pointer here, which then take the stack pointer, initialize the frame pointer with it. Then we move something here. This doesn't change anything because it's just R0, right? And then down here we have a branch link factorial. Actually, we would jump past this right now. We don't go here quite yet. So we go down to factorial. There's a line. I feel like this is an error. I don't think this is supposed to be a gap here, but even let's assume that factorial was meant to be at this store command. Store command down here stores R0 into the frame pointer -4, right? So as you just said, stores can affect it depending on where it's being stored. So in general, we think of store commands as just taking the value and putting it into memory. And sometimes we overlook the fact that push and pop aren't the only method of getting something onto the stack. It's just push and pop will shove it onto the top. Push will shove whatever you have onto the top of the stack or wherever your frame pointer is, bottom of your frame pointer. And pop will pull out whatever was, last put in. But the thing is, store, if you specify a value or a memory value, in this case frame pointer, which is on the stack somewhere, then it's still going to get sent there. Stack is just memory. We just named it. We just named a portion of memory something different and use it a little differently, but it's still memory and functions behind those same fundamental rules of if you specify an address and say put this here or pull this from here, it's going to do that. So that means store commands can affect the stack, same as this one. Any store command that has a destination of frame pointer or stack pointer is probably going to affect the stack. You can assume it will, as Ron just said. So we did it down to factorial. This is going to store R0 frame pointer. This is just -4. So the frame pointer will be subtracted by 4. So this is decrementing it and then pushing it into the next, not pushing it. This is just putting R0 into the next portion on the frame pointer or next position. And this one here is functionally this load command, this R3 frame pointer -4. So this is storing R0 into this position, and then this is loading R3 from the next position behind it. So this load command doesn't necessarily affect the stack, right? It doesn't change anything since load takes copies, right? But it does pull from the stack. So it's important to recognize where you are in the stack when that command executes, because part of stack tracing, wait, damn, I can't scroll down anymore because I am using a button. Yeah. Oh, that's just going to follow us. Part of stack tracing isn't just the stack itself. It's also register tracing. So you need to keep track of what happens across these registers. So you need to know what's on the stack in order to know what R3 is when it pulls from it, right? So there's a reason it's 30 points. Where is this? Here. Yeah, that's exactly where it was. Down. Actually, here what I'll do at this point. Clear drawings and pull this over. Oh boy. Oh, there we go. This should be the actual, this is what she wants from us for stack tracing, right? So the same command, this is 2018, this is fall 2018. So what is it, fall 2019 and fall 2018 are the best exams to review for this upcoming one, particularly the stack tracing and the function. The cube function particularly is good, but currently we're working on the stack tracing. So I'm going to go back and use the pen, and we're just going to circle everything, or put a tick mark next to everything that can theoretically affect the stack. Sub. All of this stuff changes values, which are then later on used down here actually. Load could do something, or at least you're going to have to pull from it. Let's compare as a branch any. That's branch not equal to. It goes to L4. Where even is that? Wait, does she not have the branch positions?
L4 is below line 76. it's blended in with the numbers.
Yeah, I see.
Oh, that's weird. I feel like that's not how it's supposed to be. Oh,
No,
well.
it's yeah.
Even so, yeah, so that's where that would go. Then where's L5?
108 between 108
Yeah.
and 112.
Oh
Oh my
boy, they're all like that. This sucks. All right, even so, let's just, I'm just go through all these questions. Yeah, it's like that. They did that with factorial too,
Looks like
Yeah.
L5 is just the cleanup procedure.
I suppose. Yeah, this is a little wacky. I feel like that there were some mistypes here or something.
No,
way.
it's definitely should be like right outside 80.
Yeah, it should be
First
like
year, 80.
L4, yeah, like over here or
I
something.
think in the
I know
normal
you
code it
put
would be.
it on the
Yeah.
outside.
Yeah, it's a little wacky. It is how it is, I suppose. So this is a CMP, this is a branch, which go down here. Let's just go through this. This will take data from it. This will take data from it. Blah, 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 blah. Beyond that, so everywhere where there's a tick mark, oh, this is a pop, so that's important. This also affects something because that's going to take the frame pointer copy into the stack pointer. So this is collapsing it, I believe. Yeah. And then I don't believe there's any other command that overtly modifies the stack like these. But here's the thing, like we'll see in a second when I scroll down. Wait, we'll see in a second when I scroll down. I'm gonna clear those now. That what she wants is she wants you to identify a command. In this case, the first one just so happens to be the first command that affects the stack, which is push frame pointer. And then she simply wants you to say this is the instruction and then designate what changed. So here she has a value, right? But you know, what happens with this is stuff gets carried through. So like next instruction, if you didn't modify this portion of memory, that sticks through, just like the homework. So as you continue, the stack gets, you know, chunkier, right? That's why it's called a stack. So that's important to recognize. But then you see here that I don't know if we'll be requested to do this on the exam, but she designates where in memory they're currently at. I believe this would be the stack pointer or frame.
You'd probably want to denote that.
Is this the stack pointer right now or is this frame pointer?
Hang on. SP indicated in yellow, FP indicated in blue, green indicates SP and frame value.
It doesn't matter the size where the box, like if it's big or small.
I think if you're probably just gonna want to write something like that. And what box are you referring to specifically, like this?
Like yeah, like how we know when she gave us the homework, and it's like the box so big, and then compared to this, you're like, oh
Yeah. So this for these ones on the actual exam. This is not the right one.
Yeah, because it got me confused about
This one. You'd be given this like an empty thing, right?
Yeah.
And you also be given this one. This one's relatively straightforward because this is just like program tracing. This is a little wackier because it's instruction basis, right? But yeah, so you'll be given this box. So as it said, we want to designate the stack pointer where it is at any given time, the frame pointer where it is at any given time. And then what was the other one it said? FP and green is, okay, and green's if they're overlapping, which makes sense. That'll happen near the end and then it'll just delete itself because we're done with the stack. Collapse. So that's that. Here you can see that she didn't even use all the boxes. Here she allocated 8 or used 8 and we were given 12, right? So let's go through. So she selected line 8, 12, 16, 56, 28, 40, 44, 48, right? And that's all she said for this, for full credit. So let's go back at those. 8 is the push, that's overt, because anytime you see push or pop, assume it affects the stack. Just like we only have one push and one pop, and they both show up. So those are obvious. Then we have down here, which is a sub, as Ron said, sub, add, load, store, and move, and push and pop are all things that can theoretically affect the stack, so you want to watch out for them. So 12 is a sub command that overtly affects the stack pointer. So in this one, it doesn't change anything on the stack, but it shifts where the pointer is. Hence, you have to denote it and just highlight a new zone. This moved it up by 8, right? Except here's the thing. And here's the thing, it's subtracting, but it moves up. So remember, the stack goes from high to low. So high down, low high, right? It sounds stupid, but is what it is. So here it's subtracting 8 and then re-adding it to itself to the stack, and then it goes up 2 positions because we're, we have, what is it, byte addressable, 4 bytes per.
Yep.
So it goes up 4, or every time it goes up 4, it actually goes up 1 increment at a time, right? So that's what changes here. And then add right here is green, as she said, is when they're the same. This is an add command. This is line 16, add the frame pointer to the stack pointer 0. All this is doing is saying the frame pointer is now the stack pointer. And they had to put a 0 here because in ARM assembly, your add requires something over here. But putting a 0 here functionally is just adding FP, SP, nothing else. And that's what she did, which now initializes the frame pointer to be the exact same position as the stack pointer. Still nothing has changed. Down here, we reach that store command, which stores a value in the frame pointer -4. When you subtract 4, you jump up a position, but the frame pointer itself hasn't changed positions. In reality, it's just been operated on. And then you store whatever was in there. It just so happened that if you run through this program, whatever is in, this is a store command, but I think this was in what? Our line 53 is right here. No, 56. And it was storing R0. R0 happened to have a value of 1 at that time, which will be denoted down here, I'm sure. Yeah. So that pops in. And it pops in 1 position higher than the current frame pointer location because of that little command bit. Then we go to line 28. I like that these are out of order. That's legendary. 28. But I know why they're out of order. It's because we skipped line 28 because we branched to factorial. Either way. So I don't know if she wants us to have the instructions in logical order or numerical order. I don't know if it matters, but keep in mind she did it in logic order. So you might just want to do it that way as well. And then here we reach another store command, which stores at FP. It stores R0 at FP. This would be +4. And since the frame pointer is in the same location, that means you store R0 down 1 location from where the frame pointer currently is. Minus, you store it 1 up. Addition, you store it 1 down, right? And now we're down here. Coolio. And now we have some fun stuff over here. So yellow designates the stack pointer, right? Yep. FP is in blue and green is both. So here's where they separate from one another. So the stack pointer itself, once it was, merged with the frame pointer, has not moved yet. But this next command modifies only the frame pointer. So the stack pointer sticks where it is and the frame pointer changes position. And this one's interesting because so we have the frame pointer itself and then +4 stored into itself. And it went down 2 positions. Anyone have a reason why this would be the case? Is it because of the S?
The S will just set the carry bits.
Yeah, so looking
Not
at
carry
this,
bits, but
status bits or whatever.
yeah, status bits.
So looking at this is line 40. Let's confirm that that's not supposed to be an 8, shall we? That's supposed to be an
Yeah,
8.
it's supposed
There
to
we
be
go.
an 8, yeah.
There we go. So that was just a misprint. So that's an error on her behalf on the solution bit here. But yeah, so this one is just a simple thing of changing where the frame pointer is from where it used to be here. When you add 8 to it, that causes it to go into the higher memory addresses. 4 goes down 1, another 4 goes down here. So now our stack pointer and frame pointer are in separate positions. Next command causes the stack pointer to once more collapse into the frame pointer, legendary. So once you start doing this stuff, when you start moving the stack pointer and frame pointer into each other, it means you're almost done using the stack, if not already. She called it collapsing the stack, and it's an apt term. So now here we move the stack pointer, or we move the frame pointer into the stack pointer, which means we take what was here, say, hey, go here. So it goes there, and then it goes there, and that's all it does. So that's actually interesting. So this is similar to the homework in which a lot of the stuff could just be changes of the stack and frame pointer itself and really have nothing to do with the actual values. So
yeah, I wouldn't bother on just the stack and frame pointer changes, having to recopy everything.
yeah.
That's kind of a waste of time, I think, if that's not how she wants us to do it.
So this is her solution. So I think in general, she's going to give us a program like this, which is relatively simple with regards to how it affects everything.
Right.
So in general, she gives us a max of 12 boxes, most likely.
Well, no,
And-
she did track. She tracked just simple movements of
Yeah,
the stack.
this is
Hmm.
a simple movement. This is a simple movement. This is a simple
The
movement.
second
and-
one's a simple movement.
Yeah, this is simple movement. Yeah, so there's not many commands that directly affect it. I think there's more movement.
Okay,
commands
so
than
then
anything.
disregard what I said before. Just do everything.
Yeah, just keep track of everything. That's important. Then down here is the last step, which we collapse the stack here. So we're done with the pointers. Then we go over here. We no longer need to say anything about them because we're about to be finished. And the last thing is pop FP. So it just means we take the values of them. Is this a mistype? They're supposed to be the same from this. I think this should be C.
Yeah, that should be.
Yeah, these are supposed to be the same. But even so, at the last step.
Well,
this is
actually,
a
no.
pop
Pop's
here, right?
gonna. It subtracts 4, but I forget which order it does it in.
Well, no, I was about to say when you end it, the stack point needs to be 0.
Yeah.
Oh yeah, okay, then yeah. So the termination just results in stack pointer 0 and then frame pointer sticks where it was.
Yeah.
And we pull that value, which happens to be unchanged because at the end we put the frame pointer back where it was. So technically we could have immediately said, C0000 is the frame pointer at the end if we knew that this is gonna be how it is. And then down here for register tracking, this is really, oh, and we have frame pointer changes here. And the frame pointer changes that we denote are actually, what is it? Here, 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 and here. Anywhere where there's green on this portion is when the frame pointer was altered in some way. So we have to keep track of the memory changes to the frame pointers where it's pointing. And that's what that is. The link register is because we have a function here, right? And the link register keeps track of a line, right? In the code.
Yeah, it keeps
Yeah,
track
yeah.
of the line number. The
Yeah,
things
so
to the left.
factorial is supposed to be on 56 if it keeps track of 60.
Yeah.
Yeah, that's what I thought. All right. And then, yeah, later on you load it with 28. So this one's very simple. As you can see, it doesn't run for very long. So hopefully we get something like that. For time concerns, I'm pretty sure we will get something like that. I don't doubt it. So that shouldn't be too bad. So for stack tracing, it's really just a matter of identifying what commands affect the stack and affect the frame pointer and stack pointer. Because as we see here, she wants us to keep track of that. In fact, it seems like that's more important than the actual values changing on the stack. So make sure to consider that. And then really just use the charts that are given. And then this part, which is really just program tracing again, but with a little bit of added pizzazz at the end, which is fun.
I've got an interesting question.
Yeah.
How come FP assumes the value of C000? That's outside the stack,
start-
isn't it?
No, it should start. Yeah.
Yeah,
FPZ.
right here. She
Okay.
just gave it that to start and then pushed it onto the stack, which means it gets a new value later on.
Scroll back down for a second. Let me look at that.
This or this.
Yeah, that's good right there. Wouldn't it be the memory of the frame pointer then gets moved into? Oh, I'll have to look at that on my
Are you
own.
looking at like line 8?
I'm looking at the 9 actually, because it's like move stack pointer to frame pointer, but
This is it moves and then immediately pushes the value that we just put in onto the stack.
where does it pull that value from though? Because it's got to pull that C000 from somewhere. Is it?
It's just
Where's the
overt-
command for that?
It's right here. It just is. Like
Okay,
she
it just
designates-
is?
Yeah, she just says, here's a memory, shove it in there.
Okay.
This might as well be hot dog, right? I love hot dog so much.
Yeah.
Even so, whatever, this is just like, we could do something or have a program where it's actually being pulled from somewhere else. But in this instance, it looks like for simplification's sake, she just shoved a memory address in there to initialize it.
Okay. Makes sense.
So like this could feasibly be where the frame pointer was or something else like that, whatever its past value was. But in this case, we're
Right.
addressing it something just for simplicity's sake. And then from there, when we start operating on stuff, because look, since we do this right here, so right now this is only the SP. The second we
Oh.
do line 16, and now the frame pointer's here, that means we keep track of that change. Look, FFFFF4, FFFFF4, right? So anytime an operation is
I see
carried,
where I
we're
missed
good.
my missed what I was thinking about. It's that pop at the end. I was like, how
Yeah,
could the
this.
frame pointer be like FFFFC and then somehow get to that, but it's the pop. I missed that.
The pop finishes the game off, but the
Yeah.
the frame pointer is moved into the stack pointer. Frame pointer is moved here specifically to FFFC. Then the stack pointer's
Right,
collapsed
and
onto
then
it again,
it
and then it's popped.
pops the value from that location into the frame pointer
Yeah,
and then moves it back to its original location outside
which is
the
why we
stack.
have C0, then we have location 1 frame pointer, location 2 frame pointer, and then value frame pointer again. So value, location, location, value. So keep
Okay.
track. That's important to remember, I suppose.
Yeah.
But yeah, so these things, if you get really good at identifying what commands matter, you can be very efficient about stack pointer questions. Like you could probably grind through this question in 20 minutes if you get really efficient about identifying proper commands to chart out. Because that's all it is really. There's a small element of program tracing, but I doubt she'll give us a super complex program. And this one is just a little weird because this weird factorial thing. But that's really just an indicator that jumps us around.
Really, you just have to know what command affects each register and location on the stack.
Yeah.
So if you just had to
So-
step through it and you knew that, okay, this modifies R1, this
Yeah,
modifies FP,
Q.
and just every time it changes, track
I
it.
love Q. Yeah. So what is it? Ron said, well, this is obvious. So we have push, we have pop. These are the obvious ones that
Mhm.
affect the stack. Then there's ones that we use for other purposes that can also affect the stack, which can be, subs. Essentially, any math function can affect the stack if you're operating on stack pointer, frame pointer, right?
Right.
Yeah.
So any math function, sub, add, mult, div, whatever we're using can affect the stack theoretically if we're operating on stack or frame pointer, right? So keep that in mind. Then we have move, which can affect the stack pointer by just yet again operating on the register storing the stack and frame pointers. Then we have store and load. Although here, I don't think she denoted the LDR as something that mattered. The LDR is just, this doesn't affect the stack. Let's put a thing here. So these are things that can affect the stack. This one doesn't change values. It takes copies out of the stack, but it's important for the register tracing part that you know where you are in the stack when this executes. So this still is something to remember, that loads are also important to track for these questions. But these commands overtly affect the stack because store will take values from registers like 56 here and put it wherever the frame pointer is -4. So up a location from FP, it'll shove R0 in there and so on. And move is just because, later on we do a move command that collapses the stack down here. Where is it hiding? Right here, line 44 is a move, collapses the stack on the frame pointer. So that's something to keep note of. So it's really just pattern recognition, honestly. Understanding what changes or understanding what can affect it. And then understanding how it affects it is more of just remembering how the programming language works, if anything. That's not stack related. That's just assembly language, I suppose.
Yeah.
So that's the stack. Gotta come out of the thingy. There we go. I can move this now. So that's the stack tracing. Pog. Anyone want to do? We've already looked over stuff like
Yeah,
that.
you guys have, I think in the previous session did that.
Yeah, in the weekly review, I go over in extreme detail how to do problems like this and this. But the stack pointer, like, this is the best one to go over. The stack and the function from 2019. Where is it hiding? Jesus, come on. Yeah, fall 2019, fall 2018, in my opinion, are the best ones to look over because this one has a complex program that utilizes an actual function that forces you to use branch link, which is probably what you'll want.
Mhm.
And then over here, wrong one, over here, it has the stack pointer problem, right? And this is obviously going to show up. Since we don't have any risk or pipelining, it's going to be stack pointer and functions primarily with a little bit of processor control and 3210 addressing. If I had to take a guess on the breakdown of the exam in terms of point value and problems, we can expect to see 10 to 15 points of vocab problems at the top. Or maybe like,
Probably like 5 to 8.
yeah.
Those-
These
think
don't
those-
count.
uh,
What?
I think it'll still be 5 like it always
Yeah,
is.
you're right. It's probably going to be 5. So it'll be 5 points of like vocab at the top. And then we can expect to see, a 30-point, this is the stack pointer. So take into consideration, we can expect to see a 30-point stack pointer problem. We can expect to see a 20-point 3210 addressing problem because this has appeared across most exams. I know this one's going to show up since we can't do risk yet. So this is going to have to be the thing that takes that place. And then we can expect to see a 20.1 of these, one problem of these. So far we're on what? We're on 20, 20, 30. So we've reached 75 points total. So we can expect to see the remainder of the points come in the form of.
She could ask the propagation delay question.
Yeah.
Because
would
that
be
one's kind of more of like.
Would you think that'd be
common
multiple choice
sense.
or like a 5-point gimme at the top?
Scroll back up to it. Let's see it.
Well, this is these things are risk focused.
Right, but I mean, if she gives you the delay and says, okay, well, what's going to be the propagation delay of this circuit where the most
In
time it's going
theory,
to take in one
she
clock
could
cycle?
give it to us since we have covered it in a lecture, but she's held pretty true to the if you haven't done a homework, it won't show up thing yet. So I'd bank on, and then the last thing that we're looking for is the 3210. Wait, not 3210, right? So we have the function, we have this for 30-ish points. We have this for 20-ish points, this for 20-ish points, and then we should expect to see a function writing question like this one for probably not 30 points. If anything, she might modify the she might modify this question and make it worth less. This one might make this worth like 15, 10 points and give us a simpler thing. Because this one's a little long. Because then it also asks another 50. No, that's wrong. There's another one where on another exam where it asks another 10-point question and says, write me the fetch cycle. In fact, that's probably what you can expect to see. It's probably going to be write the fetch cycle.
Oh, yeah. I need to look at that.
Yeah, but other than that, so the test breakdown is probably going to be one of each of the major topics, which is function writing, processor control, 3210 addressing, and stack tracing with a little bit of vocab. So you'll probably have, unlike last exam where there were like 16 questions because each of them was worth like 5 points. This exam is probably going to have like 10 questions max.
Yeah, I'd say less questions, but more points.
Yeah. Well, same points, but yeah, each question's worth more points. You're right.
Yeah.
Yeah. So that'll probably be how this is going to break down at the end of the day, which is fine. I prefer more in-depth questions.
Honestly, the only thing I could think of is possibly having like a little bit harder of a stack tracing question because we have less on the test.
Yeah, the stack tracing question, its difficulty truly depends on the complexity of the function she gives us that utilizes the stack. That's how it is. Because the one that she gave us in this example in the fall 2018 exam is relatively rudimentary in terms of the register portion because it only affects it 3 times and the values barely change. But we could have a more complex register, or if anything, we could have one that's multiple iterations that affect the registers multiple times while the stack remains the same. Because remember, what's the point of the stack, right? In general, we use the stack to store values while we're using a function or store values of a function to return them. So you could do a function that has multiple iterations that change intermediate registers that we're tracing, but not change the stack. So the registers, you have like 10 changes in a register and have no changes in the stack until it's done with its iterations and returns the last value you traced.
Has she given us an assignment on making a program that uses the stack?
Technically, she gave us a function assignment, and functions are like the primary use of the stack in most cases. But we didn't have to use them.
I think she said we didn't have to use
yeah, you
the
don't
stack.
Yeah, you really don't have to. You only really need to use the stack when you start. I think she said you could get away your entire life never using the stack, but sometimes it's just easier because it gets really annoying using functions and having to use a bunch of intermediate registers.
Right.
To overwrite stuff. Because here, the great part about the stack is you can, at minimum, you can use it to take values that were in the registers that you need for later, right? Remember, like the principle of C++ or principle of programming in general is when you're doing like a mathematical operation, A plus B is equal to C or something, you don't want to change A plus B. You just want C to change.
Right.
But if you're doing a function, you might have to overwrite these registers because we're limited in memory space. The only reason the stack needs to exist is because we're limited on registers. That's our problem.
Yeah.
So we have to take stuff out of the registers that we don't want to change, but we need for later, shove it on the stack for later, mess around in our function, and then take that stuff back once we're done.
Interesting.
So we don't need to use it. You don't have to, as long as you have a function that's not complex enough to absorb all of your register space, you don't need to use the stack, but sometimes it's just quicker. But in this case, we can expect a moderate level of difficulty on the stack tracing, where I would expect register tracing to only do up to like 5 or 6 iterations max, and the stack tracing to only use up to 10 boxes. That is 10 commands affect the stack. With a majority of them, as we've seen, will probably only be affecting the frame and the stack pointer and do nothing to the actual values on the stack at any given
Right.
time. So that's like the gist of the stack tracing in this instance. So it's really, the trick of stack tracing is figure out what affects it, and that's basically it. And then it's just program tracing from then on out. So that's what we can expect.
Okay. Fetch cycle. This is pretty easy. It's just the memory
Yeah.
at location of PC gets stored into the instruction register, and then PC gets incremented.
Yeah, so the fetch cycle is
It says it's incremented by 1, but shouldn't it be 4?
in yes.
I think RTL it's 1, but it's in steps of
Yeah.
4. So
Yeah, so in RTL it's simplified, but yes, in reality the PC has to be incremented since we're in byte addressable stuff by 4. So it is what it is. It is what it is.
I would suggest going through and just doing on all of the tests you can get your hands on, just the first 5 problems, and just getting all the vocabulary, because she recycles them from her
Yeah.
old exams.
Yeah, and then there's the
Like a Quizlet
so
of them.
with regard to the what are they? With regard to the fetch cycle questions. So there's the basic principle of the fetch cycle across all hardware configurations, because the fetch cycle RTL is dependent on the actual figure you're given, right? Like if you don't have an incrementer on your figure, right? Like most of the time we have a built-in incrementer, but let's look at this one that's on right here. No incrementer for the PC.
You'd have to
Yeah, got to go through the
add,
ALU.
hmm.
So that's going to change the rules, right? So it all depends on your figure.
They'd have to go through like 4 times, because there's no.
Well,
unless
this
4
thing,
comes from somewhere magically.
in reality here, you would only do it once and say +1. For RTL, it's simplified. In reality, of course, you'd be doing +4. But yeah, so it's all based on the hardware that you're given or the figure that you're given, and that can either decrease or increase the complexity of your fetch cycle if you're asked to do it. But the main rules of fetch cycle is your first step is taking a value from PC and putting it into the MAR. And then using the MAR, the MAR, not the MBR. And then this one doesn't even have, it does have an instruction register. Oh, this one sucks. This would be annoying to write the fetch cycle for, the one that's currently up on the board.
Oh, no, it has an instruction register. It's
yeah, no, it does, but it's
yeah.
at the bottom and it has no hard line from memory or MAR or MBR. So you have to go all the way around. And we don't have a multiplexer to bypass the ALU. So
it's gonna have to it's gonna have to store the value in MBR, then go through
so
there.
it looks like for this one we have a method to pass. You can use F000 or F001 to pass A or B directly through the ALU with no operation change. So that's fine, but it'd be better if we had a multiplexer to skip, but oh well.
Now the question is, if we get one of these questions, will we be able to read the the subscripts on those control?
Probably, yeah. So then the main rules of fetch cycle is you take the value of PC, you put it into the MAR, and then you take the address of you take the memory of the MAR, store it into the MBR, and then shove that into the instruction register. And while that happens, depending on the hardware configuration, in one of those phases, you can increment the PC. It could be the first phase if you have enough buses or a separate incrementer, or it can be the second phase if you don't. In most cases, you can expect the fetch cycle to hover around 2 cycles in total. So it's like T0 to T1. Sometimes it gets more complex. Like this one, I think. What do you think for this, Sydney? You think the fetch cycle will be like 3, 4? Just because we're limited on buses?
Scroll down.
Does this have a fetch cycle? I don't think this one.
I
No.
think, is this the fetch cycle? No, this is not. Okay,
Yeah, this is
never
just
mind.
something. This is a nested memory one.
Probably
Let's-
4 or 5, I'd have to
Yeah, let's
guess.
think about it. I can real quick. We'll make this the last thing we do.
I mean, if you want to be real stickler about it, you're going to have to iterate PC 4 times. You're going to use 4 clock cycles to do that. If you don't, because like in the abstract RTL, it's +1, but in reality, in like the way she'd probably want us to do it is iterate it 4 times. Or at least that's how I do it to be safe. It's like you go there.
did a squiggly to make it look different because it
Well,
didn't change
yeah.
the color. But then we have the added problem of having to increment. So I think this has to be 3 stages. Since we don't have a multiplexer to bypass the ALU, we have no choice but to, I think this is a
Ooh.
T3. Because in this case, we can't take advantage of a propagation delay with the PC and pull and increment it at the same cycle.
Yeah.
So we have no choice. This one's going to be 3 because you have 1 cycle to pull this into the MAR.
I have a
I-
feeling she'd give us one with an incrementer because
Yeah,
that would
probably.
really crowd the answer
Yeah. Then
if
we
you
have
had to
another
do it 4
cycle,
cycles.
another cycle where you go down through here and go through the ALU and store into the IR,
Actually,
and then a final cycle.
there is one where you do the fetch cycle. I know.
There is
on
one,
one
but
of the
that one was
tests.
simple. I saw it. It was a simpler one. I have them all open. I'll open that one real quick to show you what that would look like. in an
It's
example.
on test 2, November 14th, 2019, and it does have an incrementer. PC does have an incrementer.
Right here. This
Oh,
one took 2 steps.
Yeah.
And here's the
Probably not
this
too bad.
this is an ideal one because incrementer. Yeah, so this one took 2 cycles. The one that we just looked at would take 3 because that PC gets PC +1 has no choice but to be a 3rd cycle because it can't be done in parallel with any other command because it always competes for the same resources.
Right.
So it needs to be made separate. So it'll be a 3 cycle. So up to T2. So that's that. Although I think everyone probably grasps it enough by this point to be able to freestyle these things
Yeah.
if they get jumped with a unique one. Let's say unique, I suppose.
Hmm.
All right, that's that. Are there any final questions, closing comments, epiphanies? I'm trying to copy what she does. I don't remember the words. I think I just said synonyms. All
mean,
right.
Yeah, just go through the true, false, or vocabulary ones.
Yeah, best practice is as
Honestly,
Sydney
just go
says.
through all of them. Just do what you can before you take the test.
Yeah,
I would recommend
as,
not doing it like the hour before, because you'll be pretty tired by then. But
I recommend doing every single one of the practice exams, grind them out Wednesday afternoon, and then get a
I don't know
nice
about Wednesday.
and get a good night's sleep.
Man,
no,
you get that
I
all
would.
day.
No, I would say we need to start grind like today, like do a little bit Monday. I'd say grind it out Monday. Look over it Tuesday. Look over it Wednesday.
Yeah. In general, though, you see,
And then look over it. A quick 2 hours before the exam.
yeah, it's been said that this exam is harder. Like everyone always says, the second exam is much harder than the first one, and then people said the first one was particularly difficult and such. But at the end of the day, like she has past exams and such, so going over past exams is a massive advantage because not only does it get you familiar with the formatting and what she's actually expecting format wise, it also gives you good examples. But in general, a lot of people tend to lock up, like on the stack tracing assignment, that wasn't air quotes hard in terms of content, but it was confusing in terms of what was expected of you format wise.
Yeah, and also like everything I looked at to try to help me too, I looked at some of these old tests, and literally everything else had essentially the same format besides the homework assignment.
Yeah.
I even had an old homework assignment for it, and it looked like how she has it set up for the old test.
Yeah.
And
In
so,
general, yeah. So a great thing to do is to go over those past exams. If anything, if not even for, trying to understand the content, even if you feel you have a good grasp of content, it's good just to get an understanding of the format and what's expected of you so you don't get any type of test anxiety or lock up on the spot. because
Yeah.
really the biggest thing in this exam is time. That's all that really matters here. If given 2-3 hours, everyone could probably pull a 90 without a doubt, because they would have no anxiety and be able to sit there and do what they need to do. But this is a time constraint, and that's always how it is. Time is always the enemy of man. So we got to make sure we optimize and do everything properly. Like I recommend for the big ones, try to do the big problems before you do the vocab problems. Just if you run out of time, you only lose those small points at the beginning.
Well, yeah,
The big
yeah,
ones
like-
at the end.
Yeah, like I said, I'd always recommend for all the people who are doing it at home, like I'm gonna do it at home. Literally like go through the exam, see about how much you have on time wise, and set a timer. And if I on the vocab questions, I set on the first one I set 1 minute per question, so I had 5 minutes. If for whatever reason I didn't make it, if I didn't figure it out in 5 minutes, I was going to move on, Yeah, because it realistically wasn't worth that many points. I mean, granted, I think I figured it out in 2 minutes, all 5, but still.
In general, good rule of thumb is allocate a minute per point a question is worth on average.
Yeah.
You'll notice that you in that instance, how long do we have to take the test? 80 minutes?
I think
Class
so.
period about.
Is that an
80
hour and 30 or is that an hour and 20?
I think
It's an hour and
It's either-
20. Yeah, so it's 80 minutes.
80
So
or 90.
you'll notice that allocating a minute per point gives 100 minutes, which means you're 20 minutes over time. Which means in theory, if you do everything perfectly based on that allocation, you are guaranteed an 80%, right? So once you figured
Some
that portion
questions
out,
aren't going to take
yeah,
a
some questions are
minute per
fast.
point,
So that's
though.
the thing.
Yeah.
In general, allocate that for the big ones, like function questions, give it 20 minutes, like that kind of stuff. Like if you need the time, go for it. If you think you can go fast, obviously just go as
Yeah.
fast as possible.
I'll give sort of my own little. Oh, were you done?
Well, real quick,
Ethan?
I was gonna say, like, just like me, on the first exam, me and Sydney took it in person, and we walked out of that room probably 2 minutes before it's finished.
I don't remember how much time I had, but I was like waiting. I was
Oh, that's
waiting. I'm like,
cringe.
are
Cringe.
people still here? And I'm like, oh no, never mind. But
I finished right up, probably 2-4 minutes left. I didn't even know because I don't look at the clock.
Yeah. I don't know. Like I've definitely had a bunch of in-person exams. Even if I get done early, I'll literally take the last, like, say I have 20 minutes left. I'll take those 20 minutes and just start re-going over shit.
oh
too.
yeah. Double check it. That's what I do. I don't waste any, or I don't let any time go.
I never got why people would get done with the exam. Be like, all right, fuck, I'm out. It's like,
I mean, I've done that before. Sometimes it's how it is.
but I will also say this on the same token. I have gotten a question wrong because I tinkered with it when it was right the first time.
Oof.
So
Yeah.
on the same side, I'm granted it was super rare. It only happened like once or twice where I got an answer wrong because of that. But it has happened.
Yeah. All right, Sydney,
But-
you were gonna say something before.
Yeah, just a
I-
testament to like
Allegory?
working. If you like have any doubts about like, oh, I don't know if I should work all these old tests again, I would say just take it blind, or at least take it with the questions that she's going to give, because I know some of these tests have like a mix match of what's going to be on there and what's not. I'd take a test worth of those questions under the time limit, see what you get, and if you like, you'll probably get, if you have no idea what you're doing, like I was on the first test before I actually started studying for it, I got like a 75, I think. I was like, oh boy, this is not going to go well. But I kept working the exams and I started seeing what she wanted, and I could easily get like a 95 on it by the time I was done in the time limit. So do the exams and the questions she asks. It helps a lot.
It is the ideal method. All right.
Yeah.
Oh, that's that. It's dinner time now. That's what I'm saying.
Oh, I already ate.
Ah.
Now
all
I
right.
get to go help my buddy with the C++ project now. So.
Oof.
Nice. Have fun.
Unfortunate. All right.
Yeah.
Well, this should be posted by tonight, without a doubt. I'm pretty fast about it.
Okay.
All right.
See you
All right.
guys.
See you.
See ya.
So yeah,
Adios. Yo, it's
Or-
Eric.
I do have one other thing to mention.
Oh, I guess